In exactly 3 hours, 6% of Russia's entire oil refining capacity would cease to exist. Not from sanctions, not from sabotage, from 361 drones that each cost less than a used car. What happened next would rewrite the rules of modern warfare and prove that sometimes the most expensive defense systems in the world can't stop a weapon built from hobby shop parts and Chinese engines you can order online. Tonight, this is the story of how Ukraine turned commercial drones into strategic weapons capable of reaching targets 1,000 kilometers inside Russia, and why the entire Russian air defense doctrine was fundamentally designed to fail. The clock read 0147 when operators at a concealed launch facility in central Ukraine began their final preparations. Their target wasn't a military base or ammunition depot. It was the Kirishi oil refinery complex in Russia's Leningrad region, sitting nearly 1,000 kilometers from the Ukrainian border. This single facility processed 6% of Russia's total oil output. In less than 3 hours, that number would drop to zero. The operators worked in darkness, their movements practiced and efficient. They had maybe 30 minutes before Russian surveillance satellites passed overhead. Maybe less if reconnaissance drones were active in the sector. Every second counted because once those drones launched, there was no calling them back. At exactly 0200 hours, the lead operator triggered the launch sequence from inside a moving vehicle. The first FP-1 drone accelerated down its makeshift rail launcher, wings flexing under the stress of rapid acceleration, lifting off when it hit 80 kilometers per hour. Every 15 seconds after that, another drone followed, banking sharply northeast the moment it gained altitude, heading directly toward Russian airspace. The operators didn't wait to watch their handiwork. They were already 2 kilometers away, racing down forest roads with headlights disabled, using nothing but night vision equipment to navigate. Behind them, the empty launch site sat exposed and vulnerable, waiting for the inevitable Russian counterstrike that would come within the hour. But here's what makes this operation extraordinary. Across Ukraine, this same desperate race was repeating itself at dozens of locations simultaneously. Farm fields in Sumy Oblast, where operators launched from hidden underground bunkers. Highway rest stops near Chernihiv, where civilian trucks suddenly revealed concealed launch rails. Factory rooftops in Kharkiv, where maintenance crews were actually specialized drone teams working undercover. 361 drones launching in a precisely choreographed sequence. Not random, not chaotic, perfectly timed down to the second. And here's the brilliant part that would confuse Russian air defense commanders for the critical first hour. The Kirishi strike package was actually launching last. Despite having the furthest distance to travel, they would burn significantly more fuel, flying faster at 200 kilometers per hour, while drones heading for closer targets around Moscow cruised efficiently at 150. This backward planning meant all 361 drones would arrive within the same 20-minute window. Moscow, Bryansk, Smolensk, Rostov, Kirishi, all facing simultaneous attack. Russian air defense commanders would be forced to make impossible choices about what to protect and what to sacrifice. What happened next would expose why their entire defense doctrine had a fatal flaw built into its foundation. Russian podlet radar stations in temporarily occupied Donetsk detected the launches within seconds of the first drone clearing the trees. These aren't your grandfather's radar systems. They can track objects as small as a baseball at 60 kilometers distance. 35 drones climbing to operational altitude might as well have been fireworks on their screens. The data flowed instantly through fiber optic cables into Russia's integrated air defense network. Computers in Moscow began calculating intercept solutions before the drones even crossed into Russian airspace. Fighter pilots across western Russia ran to their aircraft, engines already spinning up. Surface-to-air missile batteries went to full alert status. The entire Russian air defense machine lurched into action. But they were about to discover something that would fundamentally break their strategic calculations. Russia built their air defense network to stop American B-2 stealth bombers worth $2 billion each. Their S-400 missile systems fire interceptors that cost $5 million per shot. Their Su-35 fighters burn $10,000 of fuel per hour just flying combat air patrol. Every component of their defense architecture was designed and optimized for high-value targets. But these FP-1 drones cost $50,000 to build. Some estimates put it even lower at $30,000 for the basic airframe. Do the math. Fire a $5 million missile at a $50,000 drone and you've just spent 100 times the drone's value to stop it. Let the drone through and risk losing a billion-dollar refinery. Every single option meant losing economically. This wasn't warfare anymore. This was asymmetric economic attrition on a scale never seen before. And it gets worse for the defenders. The FP-1 doesn't navigate using systems that can be easily fooled or jammed. The primary navigation receiver tracks both American GPS satellites and Russian GLONASS satellites simultaneously. If the American satellites say you're at one location, but the Russian satellites say you're somewhere else, the drone's computer knows someone is lying. It can detect spoofing attempts automatically. But the really clever part is the backup navigation system using terrain contour matching. The drone's radar altimeter constantly measures elevation above ground, comparing real-time data to stored topographic maps loaded before launch. Even with both satellite navigation systems completely jammed, the drone reads the actual shape of the Earth itself to determine its exact position. You can't spoof terrain. You can't jam mountains. Physics itself was guiding these weapons toward their targets. And the engine? A Chinese two-stroke motor you can literally order online tonight for $500. It produces 6.5 horsepower burning regular gasoline from any filling station. But that cheap engine gives the drone exactly 1,600 kilometers of range. More than enough to reach deep into Russia's interior. Ukraine didn't develop exotic military technology requiring years of research and billions in funding. They took hobby shop parts, commercial electronics, and engines designed for go-karts, then turned them into strategic weapons capable of striking targets 1,000 kilometers away. The warhead, however, was pure military grade. 80 kilograms of tetryl explosive compound that detonates at 7,900 meters per second, creating a shockwave powerful enough to shatter concrete. Surrounding the explosive core were steel ball bearings that would punch through reinforced structures at 200 meters distance. By 0215, the various strike packages had merged into one massive swarm heading east. Russian radar operators watched in mounting alarm as 361 contacts converged on dozens of different targets across western Russia. The question wasn't whether Russia would detect them. They already had every drone tracked and classified. The question was whether they could stop them all, or any of them. At 0245, the Kirishi strike package reached the Belarusian border. The main swarm of 326 drones continued eastward toward Moscow and secondary targets. This was the critical moment where the operation could succeed or fail completely. 35 drones peeled north, threading through the gap between Belarusian air defenses and Russian interceptors. If detected now, isolated from the main swarm, they would be easy prey for fighters or missile batteries. The entire northern package could be wiped out in minutes. The package immediately split into what Ukrainian tactical doctrine calls a ladder formation. It's brilliant in its simplicity and devastating in its effectiveness. The Mugen 5 decoy drones climbed to 3,000 meters, deliberately broadcasting on known Ukrainian drone control frequencies. They wanted to be seen, tracked, and engaged. These modified commercial quadcopters even carried radar reflectors, simple aluminum corner cubes that made them appear much larger on radar screens. At $30,000 each, their entire purpose was to die first and save the mission. Expendable decoys drawing fire away from the real strikers. The middle tier consisted of UJ-22 drones leveling off at 1,500 meters altitude. Some carried real 20-kilogram warheads. Others carried just ballast weights to match flight characteristics and make them indistinguishable on radar. Their role was to absorb missiles from Buk and Tor short-range systems, forcing the Russians to expend ammunition on uncertain targets. The FP-1 strikers dove to 50 meters altitude, disappearing into what radar operators call ground clutter. At this low altitude, radar beams bounce off everything around them. Trees, buildings, vehicles, power lines, all creating electronic noise that completely masks small targets. Plus, there's the physics of radar propagation itself. Radar travels in straight lines, but Earth's surface curves away. At 50 meters altitude, a small drone completely vanishes from ground-based radar systems beyond 30 kilometers. The planet's curvature itself was hiding them. But here's why this formation was tactically genius. Each altitude band defeated a different layer of Russian air defense. High-altitude Mugen 5 decoys would trigger S-400 and S-300 strategic systems designed to intercept bombers and cruise missiles. Middle-altitude UJ-22 seconds would pull fire from tactical systems like Buk and Tor. The low-altitude FP-1 second would slip through the gap between these overlapping layers, and the vertical spacing meant no single missile could engage multiple drones. A missile climbing to 3,000 meters to intercept a high-altitude decoy physically cannot simultaneously hit something flying at 50 meters. The Russians would have to fire multiple missiles at each altitude band separately. A Belarusian MiG-31 interceptor scrambled from Baranovichy Air Base, its Zaslan M radar system among the most powerful ever fitted to fighter aircraft, designed to track B-52 bombers at 300 kilometers distance. But that immense power became a critical weakness. The radar uses extremely narrow pencil beams, optimized for high-altitude searches where the radar horizon extends much further. Trying to find tiny drones flying at treetop level with a MiG-31's radar is like using a telescope to find mosquitoes in your backyard. The beam is simply too focused and too high. The pilots locked onto the high-altitude Mugen 5 decoys immediately, easy targets broadcasting their position openly. But doctrine required visual identification before engaging potentially civilian aircraft. By the time they confirmed hostile intent and received clearance to fire, the real strike package had opened a 40-kilometer gap and disappeared into ground clutter. The decoys were working perfectly, pulling interceptors high while strikers slipped through low. But the drones had just entered the densest air defense network on planet Earth. Ahead waited the S-300 battery near Tikvin, equipped with its infamous 9S-19 radar system that NATO called the cheese grater because of its distinctive appearance. What the Ukrainians knew that the Russians didn't was that this supposedly unstoppable radar had exactly one weakness, and they were about to exploit it. At 0400 hours, the package approached Tikvin, 200 kilometers from Kirishi. The S-300's 9S-19M2 radar, the so-called cheese grater, began tracking them actively. This radar seemed absolutely unbeatable on paper. It frequency hops across the X-band spectrum 100 times per second. 8 gigahertz, then 12, then 10, then 9, never using the same frequency twice in a row. You fundamentally cannot jam it because by the time your jamming system reacts and adjusts, the radar has already moved to a completely different frequency. But Ukraine had discovered its fatal flaw during previous strike missions. Every 10 seconds, the system must recalibrate its frequency hopping sequence to account for atmospheric conditions and ensure all radar elements remain synchronized. For exactly 500 milliseconds, half a second, it stops transmitting entirely while the recalibration runs. Half a second of blindness every 10 seconds. If you knew precisely when that happened, you could disappear during the gap. One Mugen 5 decoy climbed to 5,000 meters, deliberately triggering the radar and forcing an engagement. The S-300 battery engaged immediately. A $3 million 9M82M missile launched against a $50,000 drone. But in the 2 seconds before the missile impacted and destroyed the decoy, that doomed drone transmitted the radar's exact timing pattern back to the rest of the swarm. Its destruction wasn't a failure. It was a sacrifice that provided the synchronization data they desperately needed. 27 seconds later, when the radar entered its 500 millisecond reset gap, the remaining drones dove hard to 10 meters altitude. For half a second, they were completely invisible to the radar system. When the radar resumed transmission, the drones had vanished into ground clutter. The operator saw ghost returns on their screens. Maybe birds flying in formation. Maybe atmospheric anomalies creating false echoes. Without solid continuous tracks, doctrine prohibited engaging. Too much risk of hitting civilian aircraft or wasting missiles on phantom targets, the swarm had slipped through during the blindness window. But they had just entered Russia's electronic warfare zone, where GPS itself would betray them. The Pol 2-1 jamming system activated, employing a sophisticated technique called meconing. It records genuine GPS signals from actual satellites, then rebroadcasts those signals with carefully calculated time delays. The drone's receivers show them over empty fields when they're actually flying over cities. 5 minutes of position data, all complete lies designed to send them off course. But the FP-1 has a backup navigation system that doesn't rely on satellites at all. The drones switched to magnetic heading combined with counting power line crossings. Each major high-voltage transmission line between the border and Kirishi became a waypoint. 7 major power lines total, following the Moscow to Petersburg energy corridor. These massive power transmission systems were mapped before the mission using commercial satellite imagery. The drones were literally navigating by counting infrastructure that physically couldn't move and couldn't be spoofed by electronic warfare. You can jam GPS. You can't relocate a high-voltage transmission tower. 2 drones flew over an unexpected iron ore deposit that created a magnetic anomaly, pulling their compasses 30 degrees off course. They vanished toward empty forest. 3 more followed the wrong set of power lines north toward Finland, lost to navigation errors. But the lead drones confirmed their power line count matched expected waypoints. They were on course for Kirishi. The package, now reduced to 24 drones, pressed forward through thickening morning fog toward the refinery's glow on the horizon. At 0600 hours, Kirishi's industrial lights became visible against the dawn sky, a glowing complex that never sleeps, processing crude oil 24 hours a day. 4 Pantsir S-1 air defense batteries protected the facility, positioned for overlapping radar coverage and interlocking fields of fire. The 20 remaining UJ-22 drones split into 5 groups of 4. Each group targeted a different Pantsir battery. The operators watching their radar screens suddenly faced an impossible tactical choice. Their systems could track all 20 incoming drones simultaneously, but each Pantsir battery could only engage 4 targets at once before needing to reload. Those 4 missiles would need 15 seconds of flight time to reach their targets at current range. During those 15 seconds, the system couldn't engage anything else without abandoning missiles already in flight. Ukraine had turned the Pantsir's precision and automation into its greatest weakness. The system was too efficient, too optimized, too dependent on completing engagement sequences. 16 missiles launched simultaneously from 4 different batteries, their rocket motors lighting up the pre-dawn sky like an artificial sunrise. The UJ-22 drones began evasive maneuvers, diving and weaving, but against missiles capable of pulling 30 G-turns, physics heavily favored the interceptors. 12 UJ-22 drones exploded in spectacular fireballs. Mission accomplished. Their sacrifice had bought exactly what the attack plan needed: 15 critical seconds. Because while those missiles flew their 15-second journeys to intercept, while the Pantsir batteries were locked into engagement sequences and blind to new threats, the FP-1 Striker drones sprinted through the gap at maximum speed. By the time the missiles impacted their targets, the real Strikers were already inside minimum engagement range. The Pantsir systems needed 45 seconds to reload their missile launchers. The FP-1 second needed only 30 seconds to close into cannon range. The mathematics favored the attackers. The Pantsir batteries immediately switched to their twin 30mm autocannons as backup weapons, firing ahead ammunition. These are specialized shells containing 360 tungsten sub-projectiles each. The fire control computer calculates exactly where each drone will be when the shells arrive downrange, then programs the shells to detonate at precise distances, creating clouds of tungsten fragments along predicted flight paths. But Ukraine had programmed random altitude changes every 2 seconds into the FP-1's flight control software. Up 10 meters, down 5, up 3, down 8, completely random with no discernible pattern. The predictive targeting system was firing at where drones should be according to ballistic calculations, not where they actually were. 3 FP-1 second flew directly into tungsten fragment clouds and disintegrated instantly. Another caught the edge of a detonation, losing half its wing, but somehow remaining airborne through sheer momentum and desperate gyroscope compensation. 6 FP-1 Strikers cleared the cannon engagement envelope at 500 meters from the refinery perimeter. The Pantsir systems physically couldn't depress their gun barrels any lower without risking hitting their own defensive positions. They had broken through the main air defense ring. But the Russians had deployed one more surprise, a very new and very dangerous toy they'd been saving. 3 surviving FP-1 second crossed the refinery's outer perimeter fence at 0618. But they had just entered the engagement zone of Russia's newest close-in weapon system, the Derivatsiya PVO, sitting on a modified BMP-3 chassis near the main gate. Its 57mm autocannon was already tracking the incoming drones with millimeter precision. This wasn't just another anti-aircraft gun. The Derevitsia was specifically designed to counter drone swarms exactly like this one. It fires shells with programmable proximity fuses that can be individually adjusted for each shot. Here's what makes it absolutely lethal. A laser rangefinder measures exact distance to each target continuously. Then the fire control computer programs every single shell as it leaves the barrel. The shell counts its own rotations during flight, detonating at precisely the calculated distance, not on impact, in front of the target. Each explosion spreads 200 tungsten ball bearings in a 10-meter diameter sphere. The drone flies into a wall of supersonic metal fragments it never sees coming. The system's computer had already calculated a firing solution using what's called barrage mode. It would create overlapping spheres of tungsten fragments at different distances: 300 meters, 250, 200, 150. A three-dimensional grid that nothing could fly through and survive. The gun barrel elevated smoothly, targeting the lead drone at 200 meters altitude. Optimal intercept point. But the Derevitsia's designers had built in a critical safety protocol that would prove fatal. Below 100 meters altitude, the expanding tungsten fragment spheres could hit the refinery itself. Storage tanks would rupture. Volatile petroleum products would leak. The defensive system trying to protect the facility could trigger the exact disaster it was designed to prevent. The safety lockout was hard-coded into the fire control computer's operating system. No manual override existed, even in combat situations. Russian doctrine prioritized facility protection above all else. The Derevitsia opened fire at 0618. The first shell detonated 200 meters from the lead drone, too far to cause damage, but close enough to reveal the firing pattern to any observer. The second shell exploded at 180 meters. The computer was walking its fire progressively closer with each shot. The third shell would be perfect. The lead FP-1 attempted to dive lower, but its damaged control surfaces responded slowly after taking fragment damage earlier. The third shell detonated exactly 8 meters away. 200 tungsten balls expanded outward at 1,500 meters per second. The drone's plywood frame shredded instantly. Fuel tank punctured, engine torn completely from its mounting bolts. It cartwheeled through the air in a death spiral, spreading flaming debris over the refinery's outer storage area. The second FP-1 dove aggressively, reaching 120 meters altitude. The Derevitsia's barrel tracked downward smoothly, following with computer precision. At 110 meters, still firing. At 105 meters, one final shell loaded in the chamber. At exactly 100 meters altitude, the system suddenly stopped. The barrel froze in position. The final shell detonated harmlessly above the diving drone. The operator could see the drone clearly on his screens. His radar tracked it perfectly. His laser rangefinder gave exact distance. But the fire control system absolutely refused to engage. He tried manual override, denied by the computer. He tried switching to direct fire mode, locked out completely. The computer had decided that protecting the refinery from friendly fire damage outweighed the risk of letting two drones through. A decision programmed by engineers in a comfortable office, now failing in actual combat. At 0619, the first FP-1 struck the CDU-100 crude distillation unit, exactly where pre-mission intelligence had indicated the junction point. 25 kilograms of tetryl explosive detonated at 7,900 meters per second, creating a pressure wave exceeding 100 psi. The corroded pipe supports that intelligence had identified failed instantly under the stress. Crude oil at 380 degrees Celsius and 30 atmospheres of pressure erupted from ruptured lines. The superheated liquid hit air and vaporized instantly, creating a fuel-air explosion that propagated through the entire processing complex. 10 seconds later, the second drone struck Tank 47's degraded seal that had been identified through thermal imaging analysis. The accumulated hydrocarbon vapors inside ignited instantly. The floating roof, designed to prevent exactly this scenario, became a 50-ton projectile, launched 200 meters by expanding gases before crashing down and crushing the administration building. 80,000 barrels of petroleum products suddenly had no containment, feeding an exponentially growing inferno that climbed toward the stratosphere. The CDU-100 failure cascaded through the interconnected refinery systems like dominoes engineered to fall in sequence. The fractionator column, suddenly starved of feedstock, experienced catastrophic pressure drop. Liquid hydrocarbons at 380 degrees Celsius underwent instantaneous phase change from liquid to vapor. A BLEVE. Boiling liquid, expanding vapor explosion. The fractionator column itself, standing 40 meters tall and weighing hundreds of tons, split along its welded seams. The top section flew 800 meters like a giant missile before crashing into the tank farm. Secondary explosions ripped outward in all directions. The BLEV shockwave punctured 6 storage tanks simultaneously. Emergency isolation systems tried desperately to contain the damage, but it was too widespread, too fast. Pumps couldn't stop with downstream pressure completely gone. Valves couldn't close against the backward flow of superheated fluids. The automated sprinkler system had no water pressure because the mains had been severed by the first explosion. The Kirishi oil refinery, 355,000 barrels per day processing capacity. 6.4% of Russia's total refining capability. It was destroying itself from within through cascading system failures. Satellite imagery would later confirm what Russia denied for days. The CDU-100 completely destroyed. The catalytic cracker destroyed. 6 months minimum before even partial operations could resume. Full capacity might never return. Too much structural damage. Too many specialized components destroyed. Russia claimed complete interception of all drones. The inferno visible from space told a different truth. This operation fundamentally changed modern warfare doctrine. It proved that expensive, sophisticated air defense systems optimized for high-value targets have critical vulnerabilities when facing cheap, mass-produced drones. It demonstrated that commercial technology can be weaponized into strategic capabilities. And it showed that sometimes the best answer to a billion-dollar problem is 361 drones that cost less than a used car. The future of warfare isn't necessarily in the most advanced technology. It's in asymmetric thinking, in finding the gaps between defensive layers, in economic attrition that makes defense mathematically impossible. Russia lost 6% of its oil refining capacity in one night, not from sanctions imposed by foreign governments, not from sabotage by infiltrators, from drones built with hobby shop parts and Chinese engines, guided by terrain matching and power line counting, flown by operators who launched from moving vehicles and disappeared before the counterstrike arrived. Welcome to the future, where the cost of defense exceeds the cost of attack, where physics and mathematics matter more than technology, where a $50,000 drone can paralyze a billion-dollar industry. The invisible war continues.